Hello, everybody. In this lecture, we are going to present the concept of the discrete time signal that will be utilized in order to test the concept of the designed algorithm or the designed digital systems. So, in this lecture, we will here focus on the topic how the discrete time signal will be generated using the platform of the MATLAB, and basically we are focusing on the commands which will be utilized in order to generate the different types of the discrete type signals that will be utilized for the purpose of the testing the concepts or the systems which we have developed for the purpose of the processing here. Here, if we see the discrete time signal, then in the discrete time signal, we can say it is nothing but this is a conversion of the continuous time signal. As we know, whatever is the signal or the information in the real world, that is converted in the form of the electrical with the help of the sensors and the transducers. And basically, if we represent here the variation of the amplitude with respect to any variable, for example the time, then it is named as the continuous time signal. As we know, the basic definition of the signal is the variation of any physical quantity or the physical energy or the physical phenomena with respect to any one variable or the more than one variables that conveys some specific information is named as the signal. And if this signal exists for each and every variable or variables, then that type of the signal is said to be the continuous signal with respect to the variable which it is changing its value here. For example, if the amplitude of any signal is changing with respect to time, then this will be known as the continuous time signal here. Now, in continuous time signal is represented something like in this manner, that is, it is a function of the time. Here we have represented as the x of the t, and say this is the signal here, and say the nature of the signal is sinusoidal with some DC level here at the starting. So if this signal has blue in color, the signal is continuous in time, that is changing its value with respect to time, and the nature of the changing the value is the sinusoidal here. Now we can say this signal say information or the here the variation is analogous to the physical quantity. That's why this is also named as the analog signal here. Now in place of the considering the total time here, now suppose we just select here the certain here the pre-decide time. For example, if we consider the t small t as equal to the an integer of the capital T, or say the 0 or the plus minus of the t, plus minus of the 2t, plus minus of the 3t. It means in order in place of the selecting the total signal, now we are selecting here the signals for the particular time, that is the integer multiple of the capital T here. So this can also be represented as the xt, now will be represented as the x of the kt, where the k is any integer starting from 0 to up to a finite value here. Now say if we are more specifically we are interested in order to represent this one in very simple form, then that can also be represented as the x of the k here. So if we see here, then we will find in place of the continuous time signal, now we are selecting here the only the discrete values here, not the continuous values here. So this, if we and it means we are selecting here the samples of the signal, and this phenomena is known as the sampling. So what is the sampling? In the sampling, sampling is capturing a signal at an instant in time, hence taking amplitude time instances here. So here it will be known as the sampling here. And if we select here the sample time t for each and every integer of the k here, then that will be named as the uniform sampling. Uniform sampling is sampling every t units of the time here. Now the discrete time signal or the discrete time representation of the analog signal is the sequences. So here in the sequences, what is happening, whatever is the analog information that has been converted in the form of the sequence with the help of the sampling here. So, and in practical applications, we use not generally use the infinite value of the k, but that must be a finite. K is also known as the iteration here. So, for a particular algorithm, whatever is the value of the k, so many iterations will be repeated in order to complete that algorithm. So, in order to process or in order to complete the algorithm, the k must be finite. That's why here the in practical applications we process the finite length sequences, and the existing sequence is often a sampled version of a continuous time signal here. Now, if we again interested in order to represent what is the relation of the speed or the rate of the sampling and the t, then whatever is the capital T, its inverse is known as the f naught, that is named as the sampling frequency or the sampling rate here, and the capital T will be known as the time step or the sample interval. Now we are moving to the example of the mathematical representation of the analog and the discrete time signal as well as their graphical representation here. For example, as we know, if we are interested in order to represent any mathematical representation that represents any continuous time signal, for example, say we consider here the sinusoidal signal, then this sinusoidal signal is represented as the xst, that is the sign here. S represents here the sign, and it is function of the t for each and every value of the small t here, and this is equal to the x of the s sine 2 pi f s t plus phi of the s. Now here the capital xs represents the amplitude, the small fs it represents the frequency in hertz, and here the t represents the time in seconds, and the phi s represents phase in radian. Uh, and hence this mathematical equation represents the sinusoidal signal or the sinusoidal function, and graphically this can be represented something like in this manner, that whatever is the xs, here the magnitude of this one, it is a function of the t here, and how it is changing, it is changing with in a fashion of the sinusoidal function and with a here the phase of the radian here of pi s radian. So xst is represented capital xs sine 2 pi fst plus phi of s. Now, if the corresponding discrete time signal or the corresponding discrete time sequence has to be represented, or that will be named as the sinusoidal sequence. Now, how the mathematically it will be represented? It will be represented something like in this manner, that is the xs of the k. K represents here the number of the iterations, that is the here the value of the k is the integer. Again it is related to the sinusoidal sequence, that's why x s and k, and here the capital xs will become the amplitude, and the capital ns, this is the period, and k is the sample index, and the phi s is the phase in radian. Now the representation of here the graphical representation of this continuous time signal becomes something like in this manner. Here we are selecting only the sequences, that is the discrete time values of the amplitude, not all values of the sinusoidal here. Now see, this is the sinusoidal in nature, but we are selecting only the discrete value of the amplitude, the discrete value of the amplitude at the discrete time interval here. Now, coming to the some examples, for example, say if we are interested in order to represent any here the exponential sequence, and say it is the represented as the xe a to power k here, then it can be represented with the help of the MATLAB code, because we are focusing on the discussion how the different type of the discrete time signals will be generated in order to test the performance of designed digital systems, because the digital signal will operate on the discrete time signal, so there is a need of the discrete time or the signals that will be utilized as the input in order to test the performance of the designed digital system here. So here, if we are interested in order to generate any exponential function here, that is the x e a to power k, then we have to define these parameters. What is the x e and what is the small a and what is the value of the k, and then we can define the total function here, and then we have to plot the x e k with respect to each and every value of the k. That will be a representation of the exponential sequence. Now see how the MATLAB code will be written. Xe we have defined, it is assigned at the 0.8, a is assigned 0.75, that is the less than 1, and k has the values from k1 to k2, that is this is the initial value and this is the final value, and there is no gap. When we consider without any gap, then by default it considers the step size of the 1, or the gap is as equal to the 1 here. So the k1 to k2, k1 is the 0 and k2 is the 10 here. So we have defined here the x, e, a and k. Now how the x, that is the function, will be written: x e a to power k here, x e multiplied by a to power k. Again see here, we have in order to represent a to power k, we have utilized here the dot then operator. This is named as the element wise operation here. So here it is the element wise operation due to the difference in the size of the row and column of the a and k. Then we will generate here the discrete time signal, and in order to generate the stems here the discrete time signal, we can utilize a function that is named as the stem, and stem function will generate the here the discrete time sequence here. Then if we are interested in order to write the k on the x level, then we can write here the x level, and in here the bracket here in the parenthesis we will write here the in a single inverted comma is the k. Similarly, if we are interested to write x e on the y level, then this will be written here the x underscore e here. Title of this one is the x e k, that is the x e k is equal to the x e a to the power k here. Now see what will be the result here. This will be the result that will be returned due to these ports here. So after writing these ports, we can generate this type of the sequence here that can be graphically represented. And now this sequence can be utilized for the purpose of the process to the design system here. Now again, if we see, we are interested in order to generate the same kind of the sequence, but the nature of the sequence is different, and say it is the unit step sequence here. So as we know, unit step sequence exists, that is its value is 1 only when the k is greater or equal to 0, and it is the 0 for negative values of the k here. So in order to generate the here this function, we will write the code something like in this manner. First we have to define the range of the k. Here we have defined the range from -5 to the 10, and we have considered that k is equal to k1 to k2 with the step size of the 1. By default it will select 1 here, and x is a function that exists only for the k is greater than 0 or the greater or equal to 0, and it is 0 for other values here. On the x level we will write here the k, on the y level we will write here the uk, and the title is the unit step sequence, and the axis is considered here. When we write the axis, see this command x level is command that is used to write anything on the x level, similarly the y level, and the title is the command that returns the title which has to be written here. And if we are interested in order to define the range of the axes, then we have to utilize the command axis here, that is the here the range of the x-axis and the range of the y-axis. Range of the x-axis is the k1 to k2, and the y-axis is minus 0.1 to 1.1 here. Now see the result here. So here when we are using this type of the commands, we are getting here the blue in color on the graph. That is by default the color will be the blue here. If we are interested for any other color, then we have to introduce the line specifiers. Now see here, we are getting the unit step sequence, and on the x-axis we have written here the k, on the y-axis we have written here the uk, and the title is the unit step sequence here, and the axis is minus here the k1 k2, that is k1 is -5 and k2 is 10 So minus 5 to the 10, and here the range of the y is minus 0.1 to 1.1, minus 0.1 to 1.1 here. This is the value that has been represented here. Now same can be tested. That is the we can test here the codes whether after writing these codes the same sequence will be generated uh, in the MATLAB or not. So we can write the code here in the MATLAB command window, and when we write the code in the MATLAB command window, then we will find the graph here that will be generated due to the this code here. We have utilized the same code here. Now see here the graph that will be generated due to this code here. This is the graph here that we have generated here. That is on the x-axis we are writing here the k, on the y-axis we are writing here the xc, and the title of the graph is the xe k xe a to power k, and the range is that is the 0 to 10 here. And similarly here the range on the y-axis is defined up to the 0.8 here. So this is the way by which we can generate here the graph as per the code here. So if we are interested for the exponential graph, then we can write this type of the command. Otherwise, if we are interested for the here the sequence, unit step sequence, so for the generation of the unit step sequence, now we have to write this code here, which we have discussed. Now if we write this code here and say we are just dividing this graph, and again we are writing the code here, we have to write the code, then we will get here the step sequence here. This is the unit step sequence that has been generated with the help of the MATLAB command here that we have written in the MATLAB command window here. So and again whatever we have written on the x-axis is the k, on the y-axis is the uk, and so on. Again we are coming to the point in order ppt point here in order to generate the another type of the sequences. See here we have discussed these concepts. Now moving to the next PPT here. Suppose we are interested in order to generate the unit impulse sequence. Now see here, what is the beauty of this unit step sequence in comparison with the unit impulse function? Unit impulse function is continuous and that exists at t is equal to 0, but the that value is infinite, but that is not the finite. But in the case of the unit impulse sequence, this value is finite, that it exists for the k is equal to 0 and it is equal to the 1 here, and it doesn't exist for any other values of the k here. So in order to generate this unit impulse sequence here, again we have to define the k. So we have defined here the k from minus 5 to 10 as we have discussed in the case, and then we will define here the x is 1 only when the k is equal to the 0 here, and then we will generate here the stem function for the impulse sequence, and on x level we will write here the k, on y level we will write the delta k. Title is the unit impulse sequence, and axis that is the here the range of the x-axis is k1 to k2, and the y-axis is minus 0. Now this is the sequence that will be generated to these codes here, and again we can check these codes by writing these codes in the command window of the MATLAB here. So we write these codes in the MATLAB command window, and say we have removed. We will write the code here. Then this is the sequence that will be generated due to the this code. The here that is the unit impulse sequence is the title. On the x-axis we are writing that k, on the y-axis we are writing that del k, and it is only for the k is equal to 0 and the value is equal to 1. So this is the way by which we can generate the sequences that can be utilized for the purpose of the testing of the here any system which we have designed. So we are on the stage to describe the different types that can be utilized for the purpose of the testing of any sequence. And now we are going to describe here the causal signal. how the causal sequence will be generated using the MATLAB command window here. As we know, suppose we generate here one sequence xk, that is the exponentially uh, decreasing function here, damped function, damped sinusoidal function here. And we have defined here the b as equal to the 0.94, a is parameter 0.1, f is 0.32, and k has a range minus 10 to 20, having a uniform gap of the 1, and x is a function that is defined as the b to power k. Again, we have considered here the dot then operator, element wise operation, then dot multiplication, element wise operation, cosinusoidal, and then 2 pi fk. We have defined here the this was in the cosine cos 2 pi fk. We have defined the f, we have defined the k here, and then after this cosine function, this will be multiplied by a exponential function b to the power k here, where the b is defined as the 0.94, that is less than 1 here. And then we will define, so this is the function here that will be generated, sinusoidal function, that is the damping here uh, towards the 0, and the nature is the cosinusoidal. Now it is damping towards 0 because the value of the b is less than 1 here. And u, that is the unit sequence, will be generated here, and unit sequence is exist only when the k is greater or equal to the 0 here. The uk will be generated here, unit sequence. Now if we multiply this sequence, that is the exponential function that is damping towards the 0, exponential cosinusoidal signal that is damping towards the 0, with this function here. Now this function is existing for the positive and negative value, but it exists only for the 0 and the positive value. So after multiplication, we will get a function that exists only for the 0 and the positive value. So this will become the causal here. This is the concept which we have applied here in order to generate the causal sequence. So here the first the exponential cosine function is generated. Then we have generated the unit sequence, and we have generated a new function, that is the x multiplied by u. And in order to plot the graph, we have divided the total here the plot in the three sections, that is the 3 cross 1, having the 3 rows, rows number 1, 2, and the 3, and 1 column. So if we write here the 3 1 1, then it means the first space will be utilized here. Here the 3 rows, amongst the 3 rows, the first row will be selected, and for that one we will generate right here that we will generate the stem function, that the k ug, and on the y level we will write here the uk, and the font size is 14. So this is the function that we have generated for the first one, and the axis range is the, here we have defined the axis range, that is minus 10 to 20 here. And similarly we will again, if we are interested for the second one, then for the second graph we will write here the 3 1 2, that is the second one, and here on the y level we will write the x of the k. Here we have written the x of the k, and for the third graph, that is the 3 1 3, subplot command will be utilized in order to decide the place of this function here. So the third row will be utilized for this one, and on the y-axis we will write the k. And x level we are writing here the k. So here on the x level we are writing the k, and the axis of the are defined here the k1 to k in the, that is from the initial value to the final value, and y is minus 2 to the 2. So in each and every case it is minus 2 to 2, minus 2 to 2, and minus 10 to 20 here. So this is the way by which we can generate the sequence. As we know, during the time of the designing, in order to design any system that is the feasible, it must be subjected to here the causal sequence. So the causal sequence will be generated by this way, that is the whatever is the sequence, first we will generate that sequence according to the selected nature, then that will be multiplied by the unit step function, and then we will get here the causal sequence. Now again we can check these codes here, as we have described in the previous cases. These codes can be checked for the purpose of the testing whether the same sequence will be generated or not here. So we will select here the sequences, the code for the sequences here, and we will write these codes in the command window here. This figure has been removed, and we are coming to the command window, and we will write the codes, and we will get here the sequences here. The same sequences will be generated here. That is the unit step sequence UK. Here the exponentially cosinusoidal damping function xk, and then multiplication of the xk and the uk having the same range, and on the x-axis we have written the k, on the y-axis it is the different names for the different function here. Okay, so similarly we can again consider here the another functions, like the here the functions. After this one we are coming to the next point, that is related to the quantization. Yes, so far we have discussed the discretization of the any function here. Discretization means whatever is the analog or the continuous time signal that was considered for the discretization only in the time domain, or we can say we have passed those signals through a switching function, and the switching time was selected as the capital of the T here. Now, when apply this type of the sequence here, for example, say if we consider here that different type of the sequences as we if we come to the previous one, suppose B here, then what is happening? Now we will get here the different values. For example, if for this duration we have selected here the all the sequence is equal to 1, but it is not true. We will select here this value, this value, this value, this value, and so on. So after discretizing, the nature is analog here. After when we can say the signal is discrete time signal, at that time only the time in the time domain we have discretized, not in the amplitude domain, because now we are getting here the range of the amplitude here. For example, for this duration we will get the range of the values here. So that range has to be converted into the fixed level, so that that can be coded here. So getting a range into the fixed level is named as the quantization here. So just we are coming to the point of the quantization here, means what is the quantization and what is the role of this quantization. The purpose of the sampling store and process a limited number of the samples that are represented by a limited number of the digits, because infinite number are the here the stored or the transmitted. So for the purpose of the transmission, reception, storing, retrieving, and processing, there is a need of a number of the sequences here. So by using the fewer digits, what will happen? We attain the faster transmission, and smaller storage area is required for the purpose of the storing the information. But at the same time, if we are reducing the number of the samples, then its accuracy or its representation will also suffer here. So we utilize the quantized samples rather than the true samples of the infinite accuracy here. But how the choice of the digits for the quantization will be selected here. The choice of the digits for quantization should be done properly. That is, in transmitting, storing, and processing, we prefer the less number of the digits, because higher is the digits, here the poorer will be the speed of the transmitting, storing, as well as the processing here. And so the less number of the digits are required, but with too small a number of the digits, we can lose the information from the original signal. So at one side there is a need of the less digits in order to here the get the efficient transmitting, storing, and the processing. But at the same side time, if we are reducing the number of the digits, then what is happening? We can lose here the information. So it means the two opposing of to facilitate a signal transmission or the storing or the processing, and at the same time maximize the number of the digits to keep the quantization errors as low as necessary in order to preserve the information. So in neither the minimum nor the maximum, but we have to select a optimum bit. There is a need of the optimization to get the optimum number of the bits. Now, if we are interested in order to represent any signal here that represents the continuous signal, and the, at the same time we are also represented to represent the corresponding quantized signal here. Then how this can be represented using the MATLAB code here? For that purpose, we will generate here the sinusoidal signal here. That is the t is defined 0 to 30, and the x is the 0.2, that is the DC value, plus 2 sine 0.245t plus 0.15. This is the sinusoidal function here. That will be generated and represented by the blue in color here. That is the analog signal here. And say the d is 0.5, and next we'll get here the x cube. That is that it will be multiplied by the 0.5, and then we will get x, whatever is the sinusoidal signal here, that will be divided by the d, and then we will consider the rounding of that one. And then we will plot here the plot t comma x here. That will be again here the sinusoidal function. Hold on. After getting this sinusoidal function, that is nothing but whatever is the sinusoidal function x, that is multiplied by the 0.5, and it is divided by the 0.5, and after getting the rounding and multiplying the 0.5, this is the sinusoidal function here. Then hold on means this graph will be holded till the hold off here. Then we will generate here the stem function, discrete time function of the t x cube, that will be represented red in color. This is the line specifier. The first one, there is no need to specify any color, or we can say that we have not specified the line specifier here. So by default, it will select here the blue in color here. Hold up. After writing the hold up, then we will write what has to be written on the y level, what has to be written on the x level, and what are the legends. In the legends, we are writing here the two signals. One is the analog signal, and the second one is the digital signal, digital quantized signal. So we will get here this type of the signal here. That is, after writing, we will get this one here. Next is, suppose we are interested to analyze the concept of any design system here, then that system should be subjected to a practical signal. When we say practical signal, it means there must be the noise. So how the noise signal will be generated? In order to develop the model for the noise signal, there is a need of the random numbers here. Or we can say now the signal has the two sections. One is the deterministic and second one is the random. The signal that can be described by the explicit mathematical formulas is known as the deterministic signal, and deterministic signal can be periodic or the aperiodic, and periodic signal consists of basic shape of the finite duration, that is the replicate of the replicated infinitely here. And signals that cannot be described in an explicit mathematical form is called as the random signal, and also it is known as the non-deterministic or the stochastic signal here. So in order to develop the model related to the need of the random function, that will be considered to generate the random signal here. Now the signal that can be described with the help of the explicit formula, that will become the deterministic. The second one will become here the random, and for the random generation of the random signal, we will utilize here the function that is named as the RND, random function here. So if we write here the xk is defined 0 to 50, having a gap of the 1, and x is, we use here the random command rand is utilized here in order to generate the random function here, and then we will generate here the mean of this function and standard deviation of this function, and then we will generate here the stem function, that is discrete time step function related to the k and x. So what is happening? We are generating here the random function, then we are calculating the mean, standard deviation, then corresponding here the discrete time signal here, and then we are plotting here these functions. So we are plotting here the three functions. So for the plotting purpose, we have to utilize here the hold on, and then we will generate these function, standard deviation, mean, and then we will write here the hold up, and after writing the hold up, what has to be written on the X level, what has to be written on the Y level, and then we will write here the legend and the title, and we can generate this function here. So this is the function that has been generated using the command of the rand, that is the random command. So for the purpose of the testing of any signal, any system, there is a need of the signal. So if in the previous lectures we have described the different types of the analog or the continuous signal, in this lecture we tried to generate the different types of the discrete time signals which will be utilized in order to test any designed digital signal processing system or the designed digital signal processing algorithms here. So first we will here the design the algorithm, then that algorithm will be subjected to the different types of the sequences in order to analyze the performance of that digital system here. And for that purpose, there is need of the different types of the discrete time signal. So we have discussed in this one how the discrete different type of the discrete time signals will be generated using the MATLAB command. So this is about the this lecture here. Again, we can come to the another function here using the rand n. There are the two commands. One in the first one we have generated the random function. Here we can generate, if we write the rand n, then this will generate here the n cross n matrix here. So here and if we write the rand m n, that will generate the m cross n matrix here. So this is the way by which we can generate the different type of the random signal either using the rand command or using the rand n. And as we have described in the previous case, the similarly we will generate here the random function, then mean, standard deviation, and then we will write here the hold on command. And after plotting each and every graph, we will put here the hold up, and we can generate here the signal that can be utilized for the purpose of the testing. So this is about the today's lecture that we have utilized here for the purpose we have discussed here for the purpose of the testing of any design algorithm with the help of the different discrete time signals. So thank you very much. And